Right, in this video what we're going to do is revisit the graphical analysis of a truss using the method of joints. And the first thing we need to do is have our truss drawn. Now we're going to keep it nice and simple as we've been doing in class, and that is to just make it something like a 60-degree truss where all the measurements are nice and easy to work with, and we'll get used to a few of these as we go. So if I just draw up a quick truss arrangement here. Now remember, trusses are about sharing the load through members that are triangulated, the triangles making it stable structure, because triangles, you can't change the side of a triangle without shortening or lengthening either of the other sides or changing the angles. Remember, a square or rectangle can be distorted without changing the length of the members. So trusses are all about the triangles. Now in this case what I'm doing here is just making it up out of 60 degrees, nice and simple one. We've seen it many times now because I've used it a couple of times, and we'll load it and we'll put the loadings. We could make it a balanced load, in which case the next part would be really easy, but I just want to revisit how we determine the two reactions using moments. So we're going to put some forces on the top here. This is just a loading process. Loads could be anywhere really, they could be in the middle, they could be hanging off the bottom, but if we make those loads facing down, and let's call this 120, we've done this before, that's 10, just to make it a bit unbalanced. What we know from that then straight away is even if we had a pin joint over here, let's just draw that in the way we normally draw a pin joint in, and over here a roller joint, so it'll have little wheels underneath it so you'd know it was a roller, which means that that one can only provide reaction in a vertical way, because all the horizontal motion or all the horizontal loads would result in motion. At least that side anyway, so it would move that way. And we want that because we want to be able to have some degree of flexibility. We don't want complete rigidity, because rigidity is dangerous. We want to be able to deform. But on this side, we'd normally be able to show that because it's a pin joint, there might be some sort of reaction coming in here, but there are no horizontals. So we can be pretty much straight away going, okay, we know there's only a vertical going up here. But the values are going to be determined by the distribution, and we can see that there's more load on this side and less load on that side, so we'd expect this one to be smaller than this one, and it will be, as we'll do the calculations in a moment. We haven't got any measurements on here, no distances. It really doesn't matter, because if we were to determine that, say let's say it's an equilateral triangle having been 60 degrees in here, 60 degrees in here, and 60 degrees all the way around, if we make that a unit, or even let's make it simple, make it 2 units, then the line of action of that force will be acting at 1 unit away. The line of action of that one, well, the next point will be 2 units away, making the 10 3 units away, and the reaction over that side would be 4 units. Now normally what we do is we determine them, or call them one particular element. So this is going to be reaction, and we call that A. It could be left, it could be right, and that's vertical. And over here we'd say R, B, A and B, be consistent. So if you call one left, you've got to call the other one right. I just tend to use RA because RRV and RLV. You might see it that way, it doesn't really matter. Okay, so there's our truss. What do we do first? Well, I've already prepared an answer for that one very quickly, because it's something we've done many times, and that is to look first at producing a free body diagram. The free body diagram eliminates all the extraneous material. Now this stuff is not extraneous in the sense that it's not useless. It's material that we don't really need to know in order to determine the reactions. So we just create a simple diagram, and on that simple diagram we determined that, well, this was going to be 1 unit. That would mean that as each one of those units goes away, there'd be 2 units there and another unit here. They could be meters, they could be tens of meters. It won't matter, because in the formula, when we start using the moment formula, the distant elements, as long as they're relative to each other, they will determine a correct moment anyway. The only thing you can't do, of course, is you can't call it Newton meters if you wanted to determine it, unless you use meters. But for this problem, because we're going to eliminate the distances throughout, it doesn't really matter. Okay, what we did in the past is we determined to pick one side, hold one side as a pin. What that then tells me is that for this to be in equilibrium, not only do all the forces vertically and horizontal have to cancel out, you're also going to have to stop all the rotational motion. And that force over here, RBV, is the only force that can counter the turning effect that's created by the 2 going down. So now we can go through the formula. Sum of sigma moments about A in a, we call that a positive direction convention, and it's equal to 0 if we've got equilibrium. So if we've got equilibrium, here's the conditions. RBV, that's that one over there, times its distance must cancel out the other 2, which we're going to call negative forces because they go in the opposite direction to the one we've determined as a positive force. It's going to be minus 20 times 1, 20 times 1, and then minus 10 times 3, because the total distance to the 10 is 3, which gives you a formula that comes out that RBV must therefore be 50 divided by 4, which becomes 12.5. Now, the next stage of the process was that we know that all the vertical and horizontal forces have to cancel out. There are no horizontal forces, so therefore that's fine, but the verticals now have to be balanced. The sum of the verticals therefore have to equal 0 for equilibrium. RAV plus RBV, the only 2 going up, must therefore balance out the 2 going down. I put a negative sign in there just because it's easier than putting a negative over there, but it works out the same. So basically what you're saying is 30 minus 12.5, or 12.5 minus 30 minus that, comes to 17.5. That's the 2 totals. They add up to the 2 coming down. It's all in equilibrium. Once we've got that, we can return to our particular drawing situation. Well, this is the situation here. And we can translate those things onto it. So we now know that that is 17.5, and this one over here is 12.5. And this is when we start this process. Now, joints. Let's just talk again about what things are. These are referred to as members. So that's a member. A member is an element joining or between 2 joints. So this is a joint, and this here is a joint. There are positions that join members. This is another member. They're all just elements of the truss. So each one of those members can be determined individually, and they will be different. It should be logical that it's different. We've got more force acting down here being shared by 3. We've got a littler force over here being shared by 3. We've got one force here, a small force, being shared on 2, and this one here, a bigger force on 2. So there's going to be some differences between them. And this is where the analysis comes in. So we're actually looking at the truss to determine a couple of things. What we're going to determine is the force in each member and whether it's in tension or in compression. And they're important pieces of information, because when I'm designing a bridge or designing a structure, how it reacts in tension might be very different to how it reacts in compression. So knowing what forces are involved, the value of the forces and the type of force can help me design the bridge, or at least design the truss to handle the load appropriately. So I'm going to start from there. What we do is we look at the step, we're going to work through the design, working out each member graphically. So we're going to use a graphical method. So we could do this analytically, but I'm showing you the graphical method in this one. And we want to work from the material we know the most about. So work away from the ones with the least unknowns. That sounds sort of back to front. The one in which we know the most about is the one in which we know there are the least unknowns. So if I was to pick this joint and try to calculate what was going on graphically, I've got 1, 2, 3 members to calculate, and 3 members won't help me because there's too many unknowns here. I can work out, let's just sketch it for you, I'll show you what I mean. I can come down with a force, I can do that to a scale, and I can say that's 20, and that's equal to 20, and I say fine. I know the line of action of this one, I know it's going to go across here somewhere. At this stage I don't know whether it's going left to right or right to left, but there's a line of action. I also know the line of action of these two, so somewhere along here one's going to go up in that direction, and somewhere along here one's going to go down. Do I put that one over here? Do I put this one up here? And how long should they be? And what's it going to look like? So there's too much stuff going on. But if I come to this one, this is just 3 lines. It's a triangle. It's going to be much easier to work with. So all I need down here is to know a scale for the 17.5, and then one line of action. I can put it at the top or the bottom, it doesn't matter. and one member line of action here. So if I went from here up, I'm going to draw a triangle. I can close it up, which means that I can determine the length of them. So let's just do that. The simple process for that is to create a diagram for it. So we just get those guys out of the road, and I'll bring in a fresh sheet of paper, and we just draw to scale. Now, because we've got a scale there, or the one we had was 17.5, it's not too bad to just go here. Look, nice easy scale. I can use the centimeters as 17.5. So if I draw a line straight up to 17.5, that would represent the force going back up at reaction RAV. That's RAV, and it's equal to 17.5 on my scale. Now the two lines of action that we knew, and it really doesn't matter where I put them. I can put the line of action going down from here, or I could put it going up from here. I'm going to choose to go over this side just because I know that it looks better that way. I would do this more accurately when I'm doing it, but you can see that that's going to be at 60 degrees. So I would position that at 60 degrees. You can bring in that second set square process that I showed you, where you bring two set squares together and use them to ensure that you get parallel and vertical lines. Here I can bring in another one that comes off there at perfectly horizontal, and that will come across. Now, the thing is, remember that with equilibrium, and this is going back to vectors, for the whole thing to close up, the arrowheads have to go head to tail. So here we've got a head, so we're going to have a head up here because we've got a head to tail. Down there we've got a tail, head to tail, so here's the head. And this becomes important because if I go back now to the original drawing, what that tells me is that the force in this member is acting down. The force in this member, because we've just drawn it here, walks away, is heading away from the joint. Now those two pieces of information become important for this tension compression exercise. When a member is pushing towards a joint, it's being squashed because what's applying is a force at both ends of the member. So the arrowheads will translate. When I'm pulling away from the joint, the force in the joint is acting away from the joint. It will act away on this side as well from that joint, which means that particular joint is being stretched. So that's a tension member, and this is a compression member. Squashing, pulling. Should make sense, because when we did beams before, when you bend the beam, the bottom section of the beam gets longer than the top section of the beam, which means the bottom section is in tension and the top section gets compressed. So the same thing's happening with the way in which the truss is reacting. It's going to be compressed towards the top and tension towards the bottom. So that makes sense. Now, what are the values? That's easy to work out now. We've got it here. We simply measure, and because our scale was nice and easy, we've worked out that that one's going to be something in the order of like 9.2 or something around that idea. Actually, if I did that more accurately, I would come up with probably closer to 10. In fact, I did it the other night with it being closer to 10. And this one here, probably because I did that first angle not quite right. This one's coming out to around 20. I think when I did it before, when I did it more accurately, it comes out to 22. Let me just check. I've got one of the more accurate ones here. Let's have a quick look at that. Yeah, see the angle here was much better on this one. 17.5. Top one comes out to 10. And that one I've actually got it at 22. So anyway. Oh no, it's actually 20.2 because I've got it over here for the next one. 20.2. So that's all right. That's how you do that. You just work it out to scale. Now, I've got the other one worked out here, but I'll just show you how I came to that one. So I've actually got that force and that force here, but you'll see why in a moment. So let's just go back and look at that joint. Go back to the original. That joint there now has two unknowns. Before, we worked from this one, because it had two unknowns. At first, that had three. But because I now know the value of C, which we worked out from that previous one is equal to 20.2, I can now say I only need to find those two. But what's it going to look like? All right, back up to this little sketch. I now know something that's really important. That one is heading upwards. So when I went over here before and I said, which way do I put the lines of action? I now know that if I can come down 20, head to tail, one of these has got to go back up. I could have it over here, or I could have it over here. It doesn't really matter, as long as it's heading away from those joints. So what I did here, let's just jump ahead a little bit. With this one, there is my 20, this force here, going down, and then I decided on this one to draw the 20 coming up to that tail, head to tail. Now where did these two come from? These two simply are the line of action of that top joint, or that member rather, and the line of action of that member there. So those two things, the forces have to act inside the member. They can't act from anywhere else. They can't be out here. There's nothing there for them to act on or through. So the line of action of the members is the direction of the force. It's just the way, it's simply easy to work that you go, right, the force has got to react through the member. So the member itself gives you the line of action. Now it might be that it's slightly different the way the molecules or the atoms respond to the thing, but it's generally overall bulk following the line of action. So that's easy. Straight across, and this little guy here is simply that 60 degree going up. How would I do that? How did I do that? Well, again, if I just grab a sheet of blank, and I won't go to too much trouble in drawing it because we'll be here all day. Straight line went down, that was 60. I had decided, no, that's 100, that's 20 rather, and this one here, straight up at 60 degrees, which I took the scale from the previous one, 20. I don't know the line of action of that other one yet, so I just drew it in, continued it. Then I drew this one across, which I don't know the length of, but once I know the end of this, because it can only be 20.2, the 60 must start here and go back that way. Where they cross gives me the length of those two elements. So that's how I got the 2.8 and the 8.7. Now, having done that, we can move on to the next joint. Now, what is the next one? You're working your way around making sure that you reduce the number of unknowns. If I move over to this one here, I could do that now because I now have a value that I've determined for this top one because I worked out from this top view here, this one, that it's 8.7. So if I write 8.7 on there, I know that this member in here is 2.8. So there's only two unknowns over there. That's fine. The other one is I could come down here now because I know this one. I also know that I've got two unknowns because originally in the first part, this one here, I determined that that was 10. So I now have all the information I need to do either of the joints. Doesn't really matter which one you take on. So I'm just going to show you how those three will work out when you do them. This one here, this particular diagram, that one there, represents this joint down the bottom here. No, it doesn't. It's that one there, isn't it? There's the 10 going down, 7 going across, and now the angle coming down here. Surprisingly enough, that turns out to be 2.8, the same, which is probably reasonable because they're the two that are acting against each other. And we finish up finding this one over here to be 14.5. This bottom one, this bottom one down the one at the base, will come out in a moment as being 7.3 because we can check that. Now, if we come to this joint and look at the forces involved here, this is this particular one. Shows that the 2.8 coming down. Now why is it coming down? You've got to go back and look at the direction of the forces. This one was towards the joint, so it's going up, which means on here it's going up, which means down here it's going down, which means over on this drawing it's going down because I'm only dealing with that joint. And that implies that this other one must be going away to make that work. And the 7.3 and the 10 balance each other out. There's the 7.3 and the 10 over this side, 7.3 on this side. that works. This other one works as well. Now that I've got that, because now if that joint's going away, that means it's going away over here. Checking here, it's going down, going down. So everything seems to be balancing. And the last thing you can do to check it is to go over and look at the last joint, which should look very much like the first joint. It's a triangle, 12.5. We know that's 12.5, we calculated it correctly. So if we drew in a triangle with a side of 7.3 going across and a 14.5, which we worked out from the other diagram, if that turns out to be 12.5, you know you've done it correctly. Well, that's the basics of it. What you finish up with at the end of all that process is you can put down on the original all the information we've just determined. So we know a whole lot more about it. We know that this is directed towards the joints, which means they're all compression members, and we know the value of the force in them. This one here is going away from the joint, which means it's a tension member, and we know the value of the force. This guy is towards the joint, which means that's being squashed and that's being squashed, so that's actually compression. This one here though, however, is being stretched. Not by much, it's only a small amount, but that's a tension member. Here, this one's away from the joint, so we've got tension in there. Here it's towards the joint, so we've got compression in there. And here it's squashing up towards the joint, compression in there. So there's tension happening in these three members down here, compression in all the other members, and including this one here. Now if you think about it, that's not too unusual, even though you might say, well hang on, if this is bending, how come there's compression in there? Well, what's happening is the tension in this force member here is actually reacting back up and pushing that member a little bit, while it's deforming down, stretching down this way because it's a lighter load. The greater load on this side makes sense. Should, when you finish up analysing it, should look logical. Should be able to see, oh yeah, that makes sense. They have to counter each other out. These don't have to be the same, and they don't have to be the same. Just in this situation, it turns out to be that way. But these two really, I mean, you know, there's some structures where you can see that if you put other forces in or other members in, it's going to change the whole the way that works. I mentioned that in class that you really need to be aware of the worst case scenario. So a designer or an engineer would look at it and say, what's the maximum load I'm ever going to get on the bridge? Work out all my members to the maximum load. Everything leading up to that or going away from that will be accommodated even if they're variable. It's really the worst case scenarios you need to look at. But that's a way of using the method of joints, working one joint at a time, to graphically determine each of the loads in each of the members and the nature of the members. You need to practice it. We've done this twice now. This is just rehashing what we've already done, so it should be very familiar. We're going to do a lot of them before the course is over, and you'll find this is just straightforward, and you'll come back to this video and go, that's too easy, I'm not even bother watching it again. Okay?